My name is Jennifer Ngo-Anh. I work for the European Space Agency in the Directorate of Human and Robotic Exploration Programs. And I'm very honored to be here today and explain to you what we do, what kind of human research activities we do in the most extreme environment of this universe, which is space, why we support this kind of research, and where we can do this research, because we can actually do a lot of space-relevant research without having to leave Earth. So what do we do? What is our drive, and why is there a need to conduct research? These are the questions that hopefully at the end of the talk you will be able to answer also. So just to set the stage, human spaceflight is currently entering the next phase of space exploration. You might have heard or read in the media that all major space agencies, including us from ESA, we would like to go back to the moon. We would like to go back there not just for brief visits like in the Apollo program 50 years ago, but this time we would like to stay, to be able to work and to live up there safely and sustainably. And we would like to do so through what our American friends and colleagues now call the Artemis program. Artemis, by the way, was the twin sister of Apollo. Now, we do not want to go back to the moon for the sake of returning. We would like to go back there to prepare and to be ready for even more challenging missions. And that is that we would like to go back to, or that we would like to go to Mars with a human crew for extended periods of time. Now, linked to such ambitious goals are a lot of challenges that we need to address. And that is what we do with our daily work. Now, first of all, what are those challenges? Let me recapitulate very briefly so that we're all on the same page. It will probably not come as a surprise to you when I tell you that the space environment does not really offer conditions for which humans were made for. Space is actually quite a hostile environment for humans when you think about it. Space exposes the astronauts to massive radiation. The crews have to live autonomously and in isolation for a very long time in a very confining tin can. Space exposes astronauts to zero gravity conditions, which of course has an impact on their bodies. And all those very extreme conditions have a direct impact also on the feasibility and the success of the missions, of the long duration crewed missions that we are planning towards. So all those extreme conditions are what we address with our research activities of our ESA Human Research Program. So all the activities that we support through our program center around one central question, and that is, how can we make humans a spacefaring species? In other words, how can we contribute to make missions beyond low Earth orbit with a human crew a safe reality? And how can we preserve health over the entire lifetime of our crew members? I would like to take you now onto a brief journey through our various research platforms that are part of our program and show you what kind of activities we support on those. Now, the most prominent and most innovative research platform that I'm sure you all know is the International Space Station, or ISS. We love abbreviations. The ISS is the most complex research platform that mankind has ever made. And we can be very proud from ESA to participate to this greatest international project ever. As you can see, many international partners worked together for nearly 2 decades to complete one of the most ambitious engineering projects of all times. You have to remember or realize that more than 100 space flights were conducted over the course of the station's construction period to connect the different modules that had been built on different continents around the world and had never been integrated until they actually reached space. It's an amazing feat if you think about it. And since assembly was completed in 2011, a very productive research program has been implemented on board the space station that has continuously grown and will continue to deliver quite unique results until the end of lifetime of ISS. Currently, the official end of lifetime of ISS is 2024, but at the end of this year, we're going to ask member states to approve extension of the lifetime of ISS to at least 2030. From a technical point of view, we are safe to operate ISS until that time. End of last year, we actually celebrated the 20th anniversary of ISS, and with that, the ISS has been the only and the longest running microgravity research platform ever sustained in human history. Are you actually aware that the last date that all living humans were together on Earth was November 2nd, 2010? Since that time, since that date, there has always been somebody on board the International Space Station. Now, our human research program on board the ISS covers all body systems that are affected by the space environment. For example, with our research activities, we address the issue of aging. Astronauts on board the space station age much faster than people down on Earth, and that allows us to study aging processes in a very structured way. We study the muscle system of our crew members because astronauts work in a weightless environment. Very little muscle work is needed to move around. We all know that without regular use and regular exercise, our muscles weaken and deteriorate, which is something we really need to counteract against in our astronaut crew members. You probably have seen pictures from astronauts who return from their stays on board the ISS and have to be carried to their chairs for the welcoming ceremony at the landing site in Kazakhstan. Just imagine that one day we manage to land on Moon and Mars, and our crew members arrive on the surface of Moon and Mars in a state that does not allow them to carry out the tasks that they trained for. Food and nutrition are important parts of our life. The primary role of food, I don't have to tell you, is to provide us with sufficient nutrients to meet our metabolic requirements. But we know that those requirements are not met by the crew members who are on board the ISS or who are on board spacecrafts in general. So the energy consumption is well below the normal daily intake recommendations of the World Health Organization. And we all know how energy consumption or an energy deficit can affect our moods, our ability to function properly. So we really need to understand the mechanism behind this negative energy balance in space. Is it because astronauts have reduced appetite? Is it because taste and smell sensations are altered when they're in space? Is it because energy requirements of astronauts in space are reduced in general? So do astronauts in general need less calories when they're in microgravity? Do we therefore maybe need to send less food along, saving on valuable cargo mass? So these are the questions that we're trying to answer in that research area. So you see, we address a lot of interesting questions with our pool of experiments, but preparing for spaceflight is not an easy task. Sending people into space is expensive, it's dangerous. Access to the ISS is very constrained. There is huge competition amongst scientists to make use of the International Space Station for their research. And that is why we have alternative research platforms in our portfolio. That is why we make use of ground-based analog platforms in which we simulate certain conditions that are characteristic for the space environment. So we actually do not need to send astronauts into space in order to study how humans adapt to the space environment. We can do space research without having to leave Earth. We can do research on the effects of the space environment, on health and performance issues, without actually having to go into space. That is one of the strong elements of our ESA human research program that distinguishes us also from our international partners, because we offer complementary space research platforms to our science community. Like, for example, the very popular parabolic flight platform, which I always call our scientific bridge to the International Space Station. So during a parabolic flight campaign, 30 parabolas are flown on each flight, and during each peak of the parabola, roughly 22 seconds of microgravity are achieved. Just enough time to study the effects on fast adapting body systems or organs. We have been organizing parabolic flight campaigns since 1984. More than 1,000 experiments were successfully conducted during more than 7,000 parabolas, which is an equivalent to about 60 hours of weightlessness or more than 20 low Earth orbits. For our parabolic flight campaigns, we now make use of a specially configured A310 aircraft. That plane was certified about a year ago for flying parabolas that provide partial gravity levels. So we can now also fly, for example, gravity levels that correspond to lunar or to Martian gravity levels. We have done so in a special campaign last year, and we look forward to offer this very exploration relevant opportunity also in the future. We can also simulate microgravity effects here on Earth, and we do that in Bedrest Studies. You will hear later that Bedrest Studies are a very well-established model to study the effects of long-duration inactivity or disuse of muscles. So volunteers who agree to participate to our studies, they spend up to 60 days in bed, tilted towards the head end, usually at 6 degrees below the horizontal. And by doing so, the bodies of the volunteers start to adapt as if they were in space, and that allows us to mimic or to study some aspects of space travel. Bedrest studies are therefore a very valuable tool for simulating the effects of spaceflight on the human body, and we actually have a very long history of conducting Bedrest studies. But now, what do we actually gain from reproducing the effects? What is the point of making volunteers suffer? Well, we make use of the effects of bedrest on the volunteers to test promising countermeasures. We have tested a lot of different countermeasures in the past, ranging from clever exercise devices that can be used in bed. We've tested different drugs, special nutrition. But none of those countermeasures have provided us yet with the ultimate solution to counteract the effect of weightlessness on the human body. So the hunt for the perfect countermeasure continues. Now, what do you think? What is the simplest way to counteract the effects of zero gravity on the human body? Well, we can take gravity with us. Of course, it's not that simple, but we do have tools to create gravity. We can create artificial gravity. Artificial gravity is perhaps the most promising, but paradoxically the least studied method or tool for countering the physiological effects of microgravity. Of course, artificial gravity cannot solve problems like radiation, isolation, and confinement, but it has the potential to reproduce Earth-like gravity and therefore to reduce the effects of microgravity on the entire human body. We have recently put in place a new Bedrest study plan focusing on artificial gravity as the main countermeasure that will guide our activities in the years to come. And the idea is that we would like to prescribe gravity like a drug, giving it in short but large enough doses through so-called short-arm human centrifuges, in isolation but also in combination with specific exercise devices that will be mounted onto those centrifuges. We're currently in full swing preparing our short-arm human centrifuges for those future studies, in close cooperation with my colleagues from Slovenia, by the way. And if all goes well, we will start to release dedicated announcements of opportunities for those future studies by the beginning of next year that will then form the backbone of our future research activities on that platform. We also support research on the Antarctic continent, specifically on the French-Italian Concordia station. Now, Concordia station is one of only 3 research stations on the Antarctic continent that are permanently occupied throughout the entire year. The only other two research stations with permanent human presence in the middle of the Antarctic continent are the American Amundsen Scott South Pole Station and the Russian Vostok Station. All other permanently occupied bases are built on the more temperate and safer coastline. Now, the closest neighbors from Concordia Station are about 600 kilometers away to the north at the Russian Vostok Station. That actually makes Concordia Station more remote than the International Space Station. Now, why are we convinced that research activities on Concordia Station are valuable for us and for our program? Now, to put it very simple, you can essentially look at Concordia Station as a little International Space Station that was dropped in the middle of the Antarctic continent. And actually, a stay on Concordia Station resembles a lot the conditions that crew members or astronauts will have to face when they are on long-duration exploration missions. So crew members who stay on Concordia Station are extremely isolated and confined. They have to live autonomously with the same crew members for very long times, with no possibility for resupply. And therefore, Concordia Station serves as a high-fidelity analog on Earth for long-duration exploration missions, and that allows us to use results from mainly human research activities to extrapolate for missions into deep space with human crews. Now, we also support artificially induced isolation and confinement studies. Some of you may know or remember that ESA participated to the Mars 500 program through a cooperation with our Russian friends. During the Mars 500 program, we simulated a 520-day mission to Mars and back with a human crew of 6. Now, the Mars 500 program was successfully completed 7 years ago. The Mars 500 crew survived their trip. And our Russian friends have started in the meantime a new program, the Serious Isolation Program, in which they're simulating crewed, increasingly complex missions to the moon. And that is in line with the global exploration plans that I showed you earlier. We are preparing to participate to the 8-month and 12-month isolation missions of the Sirius program. Those are plans to be implemented next year and in 2022. So with these activities, we look at what isolation and confinement does to humans from a psychological point of view and try to identify countermeasures and or coping strategies. Another challenge that we need to address when we think about long-duration exploration missions with human crews is radiation. Astronauts on board the International Space Station are still quite protected from space radiation, but that will of course change when astronauts go towards Moon or Mars, or in general into deep space. Unfortunately, up until now, we do not yet have good practical and efficient countermeasures or radiation protection strategies in place. That is why we need to make use of a couple of ground-based radiation facilities, which we use within our so-called EBER program to advance our knowledge in that field. So that is another platform that helps us to prepare for our future human exploration missions without having to leave the Earth. And then finally, we also support activities that do not fit the box, that do not fit onto our traditional research platforms, but which are nevertheless innovative, promising, and very exploration relevant. Now, let me give you one example. When you think about space, when you think about the scariness of space and all the challenges and risks of space and the space environment, then dust, and specifically moon dust, is probably not exactly on your radar screens. But it's actually much more dangerous than you may realize. Because of the lack of gravity, dust never settles. So just imagine breathing all the dust in, which with each breath, 1 million tiny particles, and think about the damage it can do to your lungs. Dust is made out of tiny, sharp grains. It can be as rough as sandpaper and can therefore do quite some damage. In addition, dust is a very fine powder that can stick to everything that it touches, and it can find its way easily into basically everything, including, for example, your spacesuit. Now, the crew of Apollo 17 learned their lesson of how dangerous moon dust can be. They learned that during their mission back in 1972. So after the moonwalk, they were so eager to leave the lunar surface and go back into their lunar lander that they forgot to brush the dust off their spacesuits and off their boots before re-entering. And they brought all the dust, all the moon dust into the space capsule. So the dust clogged up their suits, it spread all over the spacecraft, and they were stuck with it on their entire journey home. And all crew members soon complained of nasal congestion, a phenomenon that we now call lunar hay fever. So the topic of lunar dust, or dust in general, is something where a very bright team of scientists is currently trying to develop models or strategies on how to mitigate the toxic effects of dust in space. I hope you now understand why we do research in one of the most extreme environments that exists. It is to enable life at the limits. And I also hope that you share my and our passion for this fascinating space program. If you have any questions, feel free to contact me during this conference, or also afterwards. I've put my contact details up here. But for now, I would like to thank you for your attention so far, and enjoy the rest of this session. Thank you.